Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Shear and Torsion, and it is going to provide you a broad overview of the concrete cracks and also the analysis of shear and torsion. I am going to give you an overview of what I am covering today's video. First at all, we will have a look at some fundamentals of the potential diagonal cracking, then move on to the analysis of shear and torsion, then wrap up with conclusions. Concrete elements must be capable of carrying shear forces caused by their self-weight and externally imposed actions. In beams, these shear forces will usually be greatest towards the support regions and will be resisted by a combination of factors. However, potential diagonal cracking will require the provision of reinforcement, will also be required the provision of reinforcement in all except very lightly loaded or minor beams. Torsional moments on a beam will produce shear stresses, which will try to cause diagonal cracking and may require reinforcement, which is additional to that required for bending and shear. In this video, we will focus on the shear and torsion. First, we will introduce the shear. This figure represents the distribution of principal stresses across the span of a homogeneous concrete beam. The direction of the principal compressive stresses takes the form of an arch, while the tensile stresses have the curve of a catenary or suspended chain. Towards mid-span, where the shear is low and the bending stresses are dominant, the direction of the stresses tends to the parallel to the beam axis. Near the supports, where the shearing forces are greater, the principal stresses become inclined, and the greater the shear force, the greater the angle of inclination. The tensile stresses due to shear are liable to cause diagonal cracking of the concrete near to the support, so that shear reinforcement must be provided. The actual behavior of reinforced concrete in shear is complex and difficult to analyze theoretically, but by applying the results from many experimental investigations, reasonable simplified procedures for analysis and design have been developed. In order to derive the design equations, the action of a reinforced concrete beam in shear is represented by an analogous chart as shown in this figure. The concrete acts as the top compression member and as the diagonal compression members, inclined at an angle theta to the horizontal. The bottom chord is the horizontal tension steel, and the vertical links are the transverse tension members. It should be noted that in this model of shear behavior, all shear will be resisted by the provision of links with no direct contribution from the shear capacity of the concrete itself. The angle theta increases with the magnitude of the maximum shear force on the beam and hence the compressive forces in the diagonal concrete members. It is set by Eurocode 2 to have a value between 22 and 45 degrees. First, we will discuss the diagonal compressive strut and the angle theta. The shear force applied to the section must be limited so that excessive compressive stresses don't occur in the diagonal compressive struts, leading to compressive failure of the concrete. Thus, the maximum design shear force VRD max is limited by the ultimate crushing strength of the diagonal concrete member in the analogous truss and its vertical component. With reference to this figure, the effective cross-sectional area of concrete acting as the diagonal strut is taken as BW times Z cosine theta, and the design concrete stress FCD equal to FCK over 1.5. The ultimate strength of the strut equal to ultimate design stress times cross-sectional area, and we can derive its vertical component, so that we obtain the VRD max equation. In Eurocode 2, this equation is modified by the inclusion of a strength reduction factor V1 for concrete cracked in shear. Thus, the equation becomes this expression, where the strength reduction factor takes the value of V1 equal to 0.6 times 1 minus FCK over 250, and putting Z equal to 0.9 times D, an approximation allowed by Eurocode 2. This equation becomes this expression. To ensure that there is no crashing of the diagonal compressive strut, VRD max should be larger than or equal to VED, the shear force due to the actions at the ultimate limit state. This must be checked for the maximum value of shear on the beam, which is usually taken as the shear force VEF at the face of the beam supports, so that VRD max should be larger than or equal to VEF, the ultimate shear force at the face of the support. Next, we will discuss the vertical shear reinforcement. All shear will be resisted by the provision of links with no direct contribution from the shear capacity of the concrete itself. Using the method of sections, it can be seen that at section XX in this figure, the force in the vertical link member, VWD, must equal the shear force VED, that is this expression. If the links are spaced at a distance s apart, then the force in each link is reduced proportionately and is given by this equation. And rearranging it, we obtain this expression. This equation can be used to determine the amount and spacing of the shear links and will depend on the value of theta used in the design. For most cases of beams with predominantly uniformly distributed loads, the angle theta will be 22 degrees with cotangent theta equal to 2.5. Next, we will discuss the additional longitudinal force. When using this method of shear design, it is necessary to allow for the additional longitudinal force in the tension steel, caused by the shear VED. This longitudinal tensile force, delta FTD, is caused by the horizontal component required to balance the compressive force in the inclined concrete strut. Resolving forces horizontally in the section YY shown in this figure, the longitudinal component of the force in the compressive strut is given by this equation. It is assumed that half of this force is carried by the reinforcement in the tension zone of the beam, then the additional tensile force to be provided in the tensile zone is given by delta FTD equal to half of VED times the cotangent theta. To provide for this longitudinal force at any cross-section, it is necessary to provide longitudinal reinforcement, additional to that required at that section to resist bending. This figure shows the variation of these functions, from which it can be seen that as theta is reduced, less shear reinforcement is required, but this is compensated for by an increase in the necessary longitudinal reinforcement. At values of theta greater or less than 45 degrees, the shear capacity of the section, based on compressive failure in the diagonal struts, is also reduced. Next, we will introduce the analysis of section subject to torsional moments. Torsional moments produce shear stresses that result in principal tensile stresses inclined at approximately 45 degrees to the longitudinal axis of the member. Diagonal cracking occurs when these tensile stresses exceed the tensile strength of the concrete. The cracks will form a spiral around the member as in this figure. Reinforcement in the form of closed links and longitudinal bars will carry forces from increasing torsional moment after cracking, by a charge action with reinforcement acting as tension members and concrete as compressive struts between links. Failure will eventually occur by reinforcement yielding, coupled with crushing of the concrete along line AA as cracks on the other face open up. It is assumed that once the torsional shear stress on a section exceeds the value to cause cracking, tension reinforcement in the form of closed links must be provided to resist the full torsional moment. The equations for torsional design are developed from a structural model where it is assumed that the concrete beam in torsion behaves in a similar fashion to a thin-walled box section. The box is reinforced with longitudinal bars in each corner with closed loops that rubs as transverse tension ties and the concrete providing diagonal compression struts. It is assumed that the concrete cannot provide any tensile resistance. Consider Figure A. The applied torque TED at the far end of the section produces a shear flow Q around the perimeter of the box section at the near end of the diagram. The shear flow is the product of the shear stress tool and the thickness of the hollow section. Hence, from classical elastic theory, the applied torque can be related to the shear flow by this expression, where AK is the area enclosed within the center line of the hollow box section. As Q is the shear force per unit length of the circumference of the box section, the force produced by the shear flow is the product of Q and the circumference UK of the area AK. Hence, if it is assumed that this force is resisted by the transaction of the concrete compressive struts acting at an angle theta together with tension in the longitudinal steel, from Figure B, the force Fs1 in the longitudinal tension steel is given by this equation. The required area of longitudinal tension steel to resist the torsion As1 acting at its design strength, Fyk, over 1.15, is therefore given by this expression. In the above equation, the torque T is the maximum that can be resisted by the longitudinal reinforcement, and is therefore equivalent to the design ultimate torsional moment, TED. Hence, we have this equation. The required cross-sectional area of torsional links can be determined by considering one face of the box section as shown in Figure C. If it is assumed that the area of one leg of a link ASW is acting at its design yield strength, Fyk over 1.15, the force in one link is given by this equation. However, if the links are spaced at a distance s apart, the force in each link is reduced proportionately and is given by this equation. The calculated amount of reinforcement must be provided in addition to the full bending and shear reinforcement requirements for the ultimate load combinations corresponding to the torsional load case considered. Where the reinforcement is known, these two equations can be rearranged for analysis purposes to give TED and theta as these two expressions. When analyzing or designing a section, it is also necessary to check that excessive compressive stresses don't occur in the diagonal compressive struts, leading possibly to compressive failure of the concrete. With reference to Figure C and taking the limiting torsional moment for strut, compressive failure as TRD max, then we have force in strut, area of strut, stress in strut, where FCK is the characteristic compressive stress in the concrete. As Q equal to TRD max over 2AK, then the above equation can be expressed as this equation. In Eurocode 2, this equation is modified by the inclusion of a strength reduction factor V1 to give this equation, where the strength reduction factor takes the value of 0.6 times 1 minus FCK over 250. The value of TRD max should be larger than TED. To calculate the torsional reinforcement required from the previous equation, we have this equation, where ASW is the area of one leg of a link. To calculate the additional longitudinal reinforcement, AS1 from the previous equation, we have this equation. From conclusions what we learned, the shear is resisted by concrete struts acting in compression and shear reinforcement acting in tension. The angle of the concrete struts varies, depending on the shear force applied. Torsional moments on a beam will produce shear stresses which will try to cause diagonal cracking and may require reinforcement which is additional to that required for bending and shear. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,